Okay. I guess I was muted. I didn't feel like I was, but I guess that I was. Apologize.
Yeah, you muted the whole time.
Well, I didn't really say anything that was earth-shattering yet, so I guess I was good. Let me start at the beginning then. In case for those of you who didn't see my message at the beginning of class and who don't read emails, spring break is canceled. So there's that. So sorry for everyone's loss on that, but it happened. Dr. Staggs was the biggest proponent of doing it, so you can direct your any issues towards him. Thank you. All right, so we're recapping Bode, right? And Bode is what? It's the graphical representation of our system as we sweep through the spectrum of frequencies, right? And so what does it represent, right? Our typical steady state equation tells us that we have these things, right? Right. We have y steady state is equal to the magnitude of my sinusoidal transfer function times the original amplitude of my input times the sine of omega t plus phi, where phi is my phase shift, right? And we can talk about these in polar form, right? Which is what we did. But really, what is this, right? What is g? Well, what is g of j omega, right? This is just the ratio of my output with respect to j omega divided by the magnitude of my input, right? So it's just my transfer function, right? It looks like that. And last class, we talked about how we can write this in polar form, right? So if we write this in polar form, we get g times e to the j phi, right? The magnitude of my transfer function times e to the j, right? That's what we get. We take this from polar and we can manipulate this in some way, right? Okay. So getting this g is important, right? So what is it, right? So if I have some vector in the real and imaginary plane, right? This vector here. If I wanted the magnitude of such a vector, right? Wouldn't I just take the real portion and the imaginary portion and do Pythagorean theorem with them? I just do a little trig. The magnitude of this vector is the real portion squared plus the imaginary portion squared square root. Right, so we'll do an example in a minute and we'll go back over all of this in a second with context on numbers. But abstractly, this is what we're doing. We're saying that there is some transfer function that has this vector in the real and imaginary plane. And because it has that vector, I know the real portion and the imaginary portion. Where does that come from? That comes from the roots of the system, right? And because I know that, then I can also figure out phi, right? Because that's just going to be the tan inverse, right? Opposite over adjacent of my imaginary divided by my real, right? And that's where phase and magnitude stem from, right? Now, what we're doing is we're taking the generalized equations for each of these, for this transfer function, and we are substituting in all omegas, and we're going to plot And we're going to see what does the magnitude look like if I vary omega, right? I vary the frequency that I'm operating at. And what does the phase look like? And that is the Bode phase and magnitude plots. Okay. We talked a little bit about it last class about what those entail, right? How we can use them. We talked one specific example. And the specific example was, given this Bode plot, can you give me Y steady state? Right? If you know the original input function, you just go into your Bode plot at omega, right? And you pick off your magnitude and your phase, and you bring phase into radians from degrees, and you make magnitude into unitless from dB. So let's talk about that. Let's talk about that really quick. Right. So remember, when we're doing our magnitude plots, we are interested in getting the magnitude in decibels, which is given by 20 log of whatever our magnitude was, right? Remember that. The reverse is also true, right? This means that G of J omega, the magnitude not in decibels, has to be, well, if I wanted to solve for this, right, I would divide by 20, right? I'll put everything to the 10th power. 10 to the log is going to give me G of J omega in decibels divided by 20. And this is the reverse. So we're just solving, just taking and solving. And remember, whenever you're doing this, you got to make sure, that you use log base 10, not natural log. Show. dB, decibels. Yes. Remember, when we're looking at the Bode diagram for magnitude, we are looking at it in decibels. We're going to watch a video that explains the history of that. Later, it has to do with when it was developed at Bell Labs and transmission units and all those things. So we'll watch a little bit of a video about that today. So stay tuned. Don't go anywhere. Okay. All right, so we're back to this, right? So Bodean resonance, and like I said earlier, we're going to talk about resonance today, so I'm not surprised that you're confused because we haven't talked about it at all. All right, you guys have any other questions, comments, concerns for right now that you want to bring up? I told you already the spring break thing, you guys had talked to Dr. Staggs about that. That was unilaterally his decision. Okay. No questions? Everybody's doing all right? Okay. Mega homework is due this Sunday. After today's class, you guys should have everything that you need to be able to finish it. You're pretty much there anyway. Hopefully you have started it. If you haven't, please start it tonight. So you can ask questions at office hours over the next couple of days, right? Office hours are from 3 to 5 today, tomorrow, and Friday. Exam 3 is on the 17th, so a week from Thursday. It's going to be on test models again. If you're a Thursday student and you want to come into the classroom to take it, you may. Bring your laptop, right, and make sure you have your charger. Sean? That is, yeah, the main thrust of it is going to be on homework 6 and 7, which is the mega homework. Right? Everything that didn't get covered on the last exam till now. But remember, right, the class has been building, so.
Yeah, obviously it's going to build into each other. I just meant like the main focus.
Yeah. And then the benchmark and the presentation. Right? You guys have any questions on any of these, office hours before, after class? Please ask me. Right? Here's the updated Tri-Quizzard standing. All right, so we've got the Zoom engineers, Dr. D, sanitizers, zero division, uncalibrated calipers, Quizzard lizards in the bag, Michael Scott Paper Company, Doctors Without Doctors, Life Livers, SDCK, Warzone, Yikes, 185.31, Swarm Lords, Matilda's, Pointy Compass, Static Waffles. That's where we're at. There's 2 weeks left, 2 more potential opportunities for points. We'll do something next class for that. And also then the final exam. So we are going to finish up at the end of the semester, right? I will post a YouTube video declaring the winner. And, we will set up a time next semester when you can get professional photos taken with your trophy. Okay? And by that, I mean, I use my iPhone and in HDR mode, which is like, it's nice. Okay. Speaking of exams, right, you guys know that the exams were graded. So how did we do? What's the breakdown? All right, so your guys' class got an average of 63.14% with a standard deviation of 17.93%. It is the highest average of all 3 of my sections. You guys did best on the op-amp problem. Right, that was your best problem, the impedance problem. And you did worst on the, that looks like the Laplace transform problem, where you were given the equation and you had to do the Laplace transform to get the response. So there's that. So unfortunately, I didn't make up the story for today. We will continue next week before the exam with the story, and then I will do a final in the announcing of the winners for the Tri-Quizzard tournament. I will tie up all the loose ends. Expect it's going to be a really highly rated video that YouTube algorithm can't take, and we'll probably shut down YouTube for many hours. There's that. Okay. All right, so let's start off by, this is part of our recap, right? So here we are. We have this problem. And I've got this RC circuit. I'm told that my input voltage is 2.4 times the sine of omega t volts. I'm given R is 4 and C is 0.003, like 4 ohms and 0.003 farads. And I want to use the Bode diagram to find the input frequency omega, where the magnitude of the output voltage, E sub C, drops to 1.2 volts. So we're going to do this 2 ways. First, we're going to do it by hand. Let's figure out what omega is, right? And then we're going to check it on the Bode diagram. Now, I realize that this says use the Bode diagram to do this, right? And that's fine. We will do that. But I want us to understand, it's just another way of going through this process of determining magnitude and phase, right? So for this in particular, right, we're going to redraw our circuit. Okay. So we're going to redraw our circuit. Well, that's looking good. we're going to do our home model, right? Because we need the transfer function. So I'm going to set my input as E in. My output was given as E sub C. Right, mathematical truths. And KVL. Right. One thing before we move on, actually, I didn't tell you guys, I haven't scanned in your test yet because I finished over the weekend, and rather than use my phone to scan all of them, which would have taken longer than I would like, I'm going to do it later today in the office and scan them. I'm also toying with the idea of maybe letting you guys see your feedback through test box. So I will announce how you're going to get your feedback, but you will be able to see what you did, and you will be able to ask any questions about grading errors that you think may have arisen. All right, so here we are. We got everything we need to build this model. It's a simple RC circuit. We've done this model a bunch, right? So we're just going to use KVL in our reduction and plug some things in. All right. So if we do that, we'll get E in is equal to R IC plus C, sorry, plus EC, which will change to E in is equal to RC E dot C plus EC. Right? There's my input-output equation. All right, so I have my input-output equation. So now what? Well, we need transfer function, right? So I've got to take the Laplace transform with 0 initial conditions. Take the Laplace transform, right? This is going to be E in of S is equal to RC. I don't know why I wrote S there because it should be C. RCS EC of S plus EC of S, making it a transfer function, right? I have output divided by input. And we get that. Okay, so there's our transfer function. This is G of S. And it's written in a really nice format for us already. The way that we develop the equation is already in standard form, right? Why is that important? Well, it's important because it tells us what tau is right off the bat, right? So that's nice. And we can plug in some things, right? So this would be 0.012 S plus 1, right? So all I did was R was 4, C was 0.003. I just multiplied them together at 0.012. Is everybody okay with getting the transfer function? You cool with that? Yeah. Okay. Next step, sinusoidal transfer function. Right. That's it. That's the sinusoidal transfer function. Right, done. So what did the problem statement ask us for? It asked us for the frequency. It asked us for the frequency when the magnitude is cut in half, right? When we go from 2.4 to 1.2 volts. Right? So remember, right? This is what we were given. Now we want to find the omega when this is 1.2 volts, right? The amplitude is 1. But we started with 2.4 volts. So how do we make 2.4 into 1.2?
Now hear me out. We divide by 2.
Close, Trevor. You actually would multiply by 1/2. It's very similar. But yeah. Right. So what this is telling us is that G of J omega is 1/2. Right. And that's great, because then we can take this here and we can set this equal. Well, not yet, right? We have to find the magnitude. So we're going to find the magnitude of G of J omega now. Okay. But we know that we are looking for the frequency for when G of J omega is equal to 0.5. Okay? That's what we know. So the magnitude of G of J omega is equal to 0.5, which is equal to the square root of 1 squared plus 0 squared, divided by the square root of 1 squared plus 0.012 omega squared. Right? I just took the real and the imaginary portion from my transfer function, right? And I took Pythagorean theorem of it, right? Why? Because remember, I drew the thing earlier, right? Well, let's draw the thing again. Here's my imaginary axis. Here's my real axis. In this case, right, let's look at the numerator. The numerator is 1, right? The magnitude of the numerator is 1. That is completely real. So here it is. Okay, that's the magnitude of the numerator, 1. The magnitude of the denominator, right, this vector, is going to be 0.012 times omega in the j plus 1, right? So it's going to be something that kind of looks like this, right? It's going to have phi denominator. This red one has phi numerator. But I think it's easy to see from this, right? It's very easy to see if we draw this out. Because it is completely real, phi is 0, right? It lies on the real axis. That phase angle for the numerator has to be 0. And it's all about just how much of it do we have, right? Which we know is 1. So that's fine, right? So we can rewrite that. That's 1 over square root of, well, I'm not going to rewrite it. What about this blue line, right? Well, it has a real and imaginary portion. So we're going to take the Pythagorean theorem of the real and the imaginary portion to get the magnitude. And we're going to take the tan inverse of the opposite over the adjacent to get our phasing. Okay. But we can just solve this equation, right? This is just 1 over the square root of 1 squared, right? So if you solve this, right, for omega, what do we get? Somebody crunch it.
You might want to check me on this. I had 144.33, but
Okay. We got 144.33. Does anybody?
please check that.
All right, Noah said he got the same. Sean said that he got it. And you know what, guys? It's 144.33 radians per second, right? So why is this important? This tells us that when we've attenuated by 50%, right? When we've attenuated by 50%, we will be at this frequency, right? At 144.33 radians per second. Now, that's great. We can do it by hand, and that's fine. But we're specifically asked to use the Bode plot to do this, right? So how do we do that? How do we do that? Here's the Bode plot. Right? We were told that we had 1/2 magnitude, right? Which we all established is G of j omega equal to 0.5. Remember, if we're talking about Bode plot, we've got to convert this to decibels, which is negative 6.02 decibels. So what do? You take the DC gain and you subtract 6 decibels from it, right? Minus 6.02. That is this line right here. And I draw a line, right? And where this intersects my Bode plot, I will come down and I will read my frequency off. And that happened at 144.33 radians per second. Like we calculated. Right? So, what's the point, right? Why would you want to do this? This is very similar to what we're going to talk about later with bandwidth, number one. But if you know that you want to keep your system from attenuating by a certain percentage, right? Say 1.2 volts amplitude isn't enough to run whatever device you're trying to run with this circuit. You need to be below 144 radians per second in order to get the voltage you want, right? What if we wanted, let's say, we'll talk about this in a second. I'm going to do this the other way. So when we're designing things, when we look at the Bode diagram, this is nice, right? Because I know that if I am above omega here, above 144, I will have less signal attenuation than 50%. dB. Oh, no, sorry. That log is 10. Right. Now, we didn't talk about it, but omega C is 83.33 radians per second. What is that? That's 1 over the time constant, which we said was 0.012. And if you put it in your calculator, 1 over 0.012 is in fact 83.33, right? So what if I wanted to draw the Bode asymptotes for this, right? Well, remember, my system was 1 over 0.012 S plus 1, which means my DC gain was what? Well, if I put 0 in for S to get my DC gain, it's 1 over 1, that's 1. Log, 20 times log of 1 is 0. So here's my low frequency asymptote, right, at my DC gain. The corner frequency, which we found, is going to be here, right, 83.33 radians per second. And then my high frequency asymptote decreases at minus 20 dB per decade, right? And those are all from the rules for drawing asymptotes for a first order Bode plot that we talked about last time. Also notice, we cross minus 45 at our corner frequency, just like we said we would, right? Remember, we go from 0 to minus 90 asymptote for phase for first order system. We cross minus 45 at our corner frequency. Okay. Is everybody okay with this, right? This is different, right? Because we're not necessarily calculating anything. And so I think it's important that you are able to read a Bode diagram and understand what it is telling you. It is more important for you to be able to read it than it is for you to be able to draw it. Although you will have to draw, right? Because if you look at the homework, you're gonna have to draw. Or the asymptotes for one, right? You can't really draw one. I mean, I guess you could if you wanted to get your graph paper out and really go to town with your log scale and all that. Well, like I said last class, right? If you ever need to do any sort of analysis with a Bode diagram, you'll just use a program to get it, right? But being able to draw the asymptotes helps us understand how the system is supposed to behave. Right? Okay. So really forgot where I was going with that, to be quite honest. I got caught monologuing. So so far, what have we seen? What can we do with Bode plots, right? You can determine the steady state response given an input function from a Bode plot, right? Because if you can figure out G of j omega, right, which is just my magnitude, all you have to do is convert it from decibels back into unitless. And you convert degrees into radians, right? Just read it right off the plot at the specified frequency. We can also do stuff like this, and this is interesting because it brings in the natural dynamics of this system, right? And the output voltage is reduced by 1/2 at 144 radians per second, which is 23 hertz. And this is a low pass filter, right? Why is this a low pass filter? Well, it allows at low frequencies, it allows us to keep any signal from being attenuated, right? But once we hit the break or the corner frequency, we start to get attenuation of our signal. So things that happen at high frequencies get attenuated, right, or go away, essentially. The amplitude goes away. Things that happen at low frequency maintain their integrity, right? Okay. Do you guys have any questions about this? So what would a high pass filter look like if this is a low pass? What would a high pass filter do?
It'd be like the mirror of the low pass.
Right. It would be attenuate at low frequency and allow for high frequency things to pass through, right? So the natural dynamics of this circuit, right? The natural tendency, right? Because we haven't put a control system on here. We're just looking at the open loop model for this. The natural tendency of an RC circuit is to serve as a low pass filter, which is pretty interesting. Now, there's also mechanical systems that act as low pass filters, right? Like your car suspension. I used that example last class, but your car suspension acts like a low pass filter. It allows in things like speed bumps and potholes, and it filters out things like asphalt unevenness, right? So let's try something a little bit different with this same circuit example, okay? So I've got the same exact circuit, same values and everything, but I'm changing my input. And my input is a low frequency signal, E sub s, that happens at 2.4 sine 10t, and a high frequency noise signal that's 0.2 times sine 800t, right? So it's low amplitude to begin with, but very high frequency, right? So typical background noise stuff, right? Typical background noise stuff. Right, and so notice our input E in is just the summation of these two things, our signal plus our noise. And so I can test this in Simulink pretty easily. So I've got my sine wave, 2.4 sine 10t on the top there. I'm adding to this. And so here's this is E sub s, right? This is E sub n. And once I add them together, this is E in. I know these are all labeled next to them, but I labeled them anyway for reasons. Okay. So I'm going to add ES plus EN, or ES plus EN to get E in. And then I'm going to run that through my transfer function, right? My 1 over 0.012s plus 1. And the output's going to be E sub c. That's just what our model showed. So let's take a look at this, right? So if I plot E in, right, I'm going to plot ES and E sub n together on the same plot. And the top one is kind of hard to see any differentiation, right? Because it's kind of dominated by the noise here, right? But if you come down to the second plot here, or if you come down to the second plot, you come down to the second plot, what do we have? We have this dashed line here, right? And that dashed line is E sub s, right? It's hard to see. So here's E sub s, right? So this red line. And E in is the summation of ES and E noise, right? So that input that we're giving it is this really noisy sine wave that follows the path of the signal. I don't think that you guys are any strangers to why noise is not fun, right? You've taken instrumentation, right? The HVAC in these buildings is not accommodating for getting clean signals by any means. If you ever do any human subject experimentation, you guys may or may not know this, but the human body has tremors associated with it at medium to low frequency, medium to high. Like forgetting the number off the top of my head, which is problematic. But if you ever have somebody holding something, right, your hand is kind of always shaking a little bit. Okay. And that's the type of noise that propagates into signals if you're ever doing like force or grip manipulation data, right? But anyway, this is a noisy signal, right? We've all seen a noisy signal before. So how do we deal with it, right? Well, we can run it through our low pass filter, right? Because we want to get rid of the high frequency stuff and want to keep this low frequency noise. And so if we run this through our low pass filter, this is what we get. The solid line being our signal and the dashed line being E sub c, being our output. And you can see we haven't attenuated this signal at all, right? We haven't attenuated it. It's still there, but we have phase shift by a slight amount. So by running this through the low pass filter, we've proven that the low pass filter works, right? But why does it work? Can we learn anything from the Bode diagram about why this works? And the answer is yes. So here's our Bode diagram, and you can see I've marked off on each one, right? I've marked off two frequencies. The first is 10, right? And the second one is 800, right? And so here's 10, here's 800. This intersects my Bode diagram at 0 dB. 0 dB is equal to a gain of 1, right? 0 dB is equal to a gain of 1. Which means that it hasn't amplified or attenuated, it stays the same, which is what it showed us exactly. And we've got a phase shift of like 7.5 degrees, right? Which would be a very small phase shift in radians. Similarly, if we look here, we're at roughly negative 20 dB. Negative 20 dB should be roughly 0.1. and we have a large phase shift. But for something like this, we don't really care about the phase shift, right? Because we wanted to get rid of the noise anyway. So if you can decrease your amplitude by enough, do you really care what the phase shift is, right? We're ignoring it essentially anyway. So we don't really care. Right? So by looking at a Bode plot, we can tell whether something attenuates signals at high frequencies, low frequencies, medium frequencies, right? We can do all sorts of filtering techniques that you guys have probably heard of: high pass, low pass, band pass, stop gap, stop pass, right? All these. We're not going to get into like Butterworth filters or Chebyshev filters or anything like that. Those are just different techniques for doing band pass or high pass or low pass filtering. It all depends on what order system you're trying, or what order filter you're trying to create. So we can tell quite a bit about a system in terms of how it's going to handle different frequency inputs, and what we should expect to get out of it, right? And this also allows us to see from just the natural dynamics of a system what kind of operating ranges we have, right? Because you should know roughly what kind of signal loss is acceptable for your specific application, right? Is it 25%? Is it 10%, right? How much attenuation are you willing to have? Or can be handled as part of your system, right? Wrong keyboard. Sorry. All right, you guys have any questions on applications of Bode plots? The applications stay the same whether it's first or second order, but the shape of the Bode diagram changes somewhat. They're a little bit more interesting when we get to second order. Okay. You guys have any questions? Everybody doing okay? Maybe, maybe not. No questions. All right. Second order, then. Let's go up. So let's just say, for example, we have this system here, right? In general, the standard form of a transfer function in second order is this, right? K omega n squared over s squared plus 2 zeta omega n plus omega n squared, right? This is my standard form where K is what we call the gain of the system, and is essentially just the DC gain of the system. So if we set K equal to 1 and our natural frequency equal to 10 radians per second and zeta equal to 0.2, we would get this equation out here: 100 over s squared plus 4s plus 100, right? And again, we got to find our DC gain, right? So what's the DC gain? Well, it says there that it's 1. Is that true or false? How would you check it?
Are we gonna plug and chug, solve for something?
Sure. What is the something?
What is something?
What are you plugging and what are you chugging? John.
Is that for
Okay. It's given, but how would you check it? How do you get to that answer? There it is. Yes, you plug in 0 for S. Plug in 0 for S. If you do that, what are you left with? You're left with 100 over 100. Or, as some people call that 1. Some people call that 1. Okay. So what are the rules, right? Because we have rules for first order Bode cost, so there's obviously rules for second, and they're kind of similar. The first one's exactly the same, right? You have a low frequency asymptote at the DC gain of the system in decibels, right? So in our case, right, I realize that you guys can't see what's going on here. So give me 1 second. This system was 100 over 4s squared plus 4s, s squared plus 4s plus 100. There it is. Okay. All right. So we have a flat low frequency asymptote that exists at 20 log k. All right, 20 log k, in this case, well, k was 1, 20 log of 1 is 0, 0 dB. Right, so there's my low frequency asymptote, right, at 0 dB. Great success. What's rule number 2? The high frequency asymptote exists with a slope of minus 40 dB per decade. That one is a little bit different than rule number 2 for first order, right? Rule number 2 for first order was minus 20 dB per decade. Turns out that every order that you add increases the attenuation by 20 dB per decade. So first order 20, minus 20, second order minus 40, third minus 60, fourth minus 80, so on and so forth forever, right? Till the end of time, or until you get tired of doing that. Which for me was 4. So we got minus 40 dB per decade. Right, and then we have a low frequency and a high frequency asymptote that intersect at the corner frequency, which in this case is omega n. So if you know the natural frequency for a second order system, you already know the corner frequency. In our case, we had 100 over s squared plus 4s plus 100. And omega n is 100 squared, which is 10. Which is 10. And since that's our corner frequency, we have a line of slope minus 40 dB per decade. That's our magnitude and phase asymptotes, right? Or our magnitude asymptotes. There's also one other thing that's written there. It's less of a rule and more of a, well, we'll get into it in a second, right? Number 4 says that the peak magnitude increases as damping ratio decreases. So we'll talk about that in a sec. These are all my magnitude rules, and these are all my phase rules, right? 5, 6, and 7. What's the deal with phase? Phase goes from 0 to minus 180, right? Oh, that's probably not good. Was that me? Was that somebody else? Something unplugged. You guys hear me? Do I sound like a weird robot? Okay. Right. So we go from 0 to minus 80 at low to high frequency, respectively. we cross minus 90 at our corner frequency, right, at omega n. And the sharpness of our transition depends on the damping ratio. We'll talk more about that in a second, right? But this in general, right, is gonna look something like that. And so if we drew it out, we get something that looks roughly like this, right? Kind of. No. Angle one. Yeah. There we go. That's a little bit better. No. All right. That's what we've got. Right? That's what it would look like, asymptote wise. Okay. So those are the rules. That's how we do it. Right? This is what we just drew. Here's my low frequency asymptote right here. Here's my high frequency asymptote right here. That's my omega C. Check out my phase diagram. My phase diagram crosses minus 90 at 10. Right, it goes from 0 to minus 180. What if you had higher than a second order system? Well, third order system, every time you add a system, you increase the amount of phase that's possible by minus 90 degrees. Right, so if you had a third order system, you'd have minus 270, fourth minus 260, so on and so forth. Right? Okay. Right, but I said that we would talk about that whole zeta comment, right? So let's talk about the general shape here. The general shape here. Well, how is this different than a first order? Well, a first order just had this nice kind of curvature to it, right? Had this nice curvature to it, kind of stuck to the asymptote very well, right? Well, second order system is going to have a spike. It's going to be level, it's going to spike, and then it's going to come back down to attenuation, right? Okay. Why is that, though? Why is that? Well, that has to do with the damping ratio. Has to do with the damping ratio. Turns out that as the damping ratio increases, we will force our system to look more and more first order. Hopefully, this tracks with what you guys know about when we talked about damping ratios to begin with, right? So, bless you. If you are underdamped, right, you're going to have some kind of overshoot. You have some underdamped's going to have this nice sinusoidal look to it. If you are overdamped, like zeta greater than 1, you're going to look first order, right? Turns out it's the same thing for Bode diagrams. So as zeta increases, right? So what does zeta of 0 mean? Zeta of 0 means that there's no damping whatsoever. Right? Larger amounts of zeta mean that there's more damping. More damping means that you have more attenuation, right? Means that it's harder for it to oscillate, which is what this is showing us, right? It's showing us that we're going to drive, with more damping, we will drive to attenuation quicker, right? What about phase angle? Well, the steeper the transition, the lower the damping ratio, right? So at a low damping ratio, you will maintain your phase for longer. Okay? Then all of a sudden it will drop off very quickly. Right? So zeta of 0.1 here, right? You're holding pretty steady. You're still decreasing, but you don't hit minus 45 until almost 100 radians per second. Whereas in all the other cases, right, this is a much smoother decline, but you lose more phase early, right? So whether or not time lag is important depends on whether you want high or low damping, right? The lower your damping ratio, the less lag that you're going to have in your system at lower frequencies. We're going to talk more about some of the implications of this towards the end of the class as well. Okay? All right, so here are the rules again, just to recap. Right? Flat low frequency asymptotes in decibels at a decent gain. High frequency asymptote with minus 40 dB per decade. That starts at the corner frequency, which is my natural frequency. The peak magnitude increases as the damping ratio is decreased. The phase angle starts at 0 and moves to minus 180. The phase angle shows a sharper transition for as zeta decreases, right, for lower zeta. And the phase angle of minus 90 happens at omega c. Okay. Sometimes MATLAB does some really fun stuff. Okay. Sometimes MATLAB does some really fun stuff. And it plots phase like from 90 to minus 90 instead of from 0 to 180. Just be aware that that happens sometimes. Well, depending on whether or not you have, like, so, all right, so what's the one thing that's in common with all of these systems that we've talked about, right? The biggest thing so far is that none of them have had any zeros, right? We've only had poles. We've only had denominator, S in the denominator. What happens if you have S in the numerator? We're really not going to talk about it too much, right? And it doesn't really affect magnitude, right? Because magnitude, I feel like that's the straightforward calculation, right? Magnitude. But where it really takes effect is in phase, okay? Because now instead of 0 minus something, you get something minus something else, right? Because if you have an imaginary portion in the numerator, you've got tan of something over something, right? And it starts playing with your Bode phase more than your magnitude. Just be aware that if you see an S term in the numerator, then it could make your phase look weird. No, all right. You guys have any questions so far? We're doing okay. Everybody's all right. Tracking, kinda. You said we would talk about resonance, but we didn't talk about resonance yet. Jeez. Take it easy. Your resonance, people. Gosh. Fine. You want to talk about resonance? Jeez. We'll talk about it so bad. We'll talk about it. What is resonance, right? I think this is a term that gets thrown around pretty frequently. Yes. Excellent. High frequency indeed. The resonant frequency is the frequency in a system where we have the maximum amplitude. Okay. So if you're looking at a Bode diagram, let's go back to the one we had earlier. This one. Right? Your resonant frequency happens at peak magnitude. So if you were given a Bode diagram, how would you find the resonant frequency? You just go to wherever the maximum magnitude is and you drop down and tell me what the frequency is, right? But what if you weren't given that and you wanted to calculate it? Well, we have this equation here, right? Let's talk a little bit about resonant frequency, right? When the input frequency is near the corner frequency, the magnitude ratio depends on zeta. As zeta goes to 0, the magnitude becomes infinite. When the input frequency matches the undamped natural frequency, resonance occurs. As damping increases, the resonant peak on the magnitude diagram goes down. Right? So as we, yeah. Okay. As damping increases, the resonant peak on the Bode magnitude plot decreases, right? We've seen that. It kind of squashes it down, right? Squashes it down. The amplitude ratio is the maximum at the resonant frequency, right? And here's the equation. The resonant frequency, omega r, is equal to the natural frequency times the square root of 1 minus 2 times zeta squared, right? So a couple of notes about resonant frequency. 1, when zeta is equal to 0, the resonant frequency is equal to the natural frequency. When there's no damping, the resonant frequency and the natural frequency are the same. Resonant frequency is always less than or equal to omega n, right? I mean, if you look at this equation, I think that makes sense. But Dr. D, what if we have negative zeta? Impossible. Impossible. Cannot have negative zeta. Makes no physical sense. If zeta is greater than 0.7071, there is no resonant peak. It's a magic number. Right. You guys have any question on resonance as it is? What about bandwidth? Talk about bandwidth. In order to talk about, so what is bandwidth? Bandwidth is a range of frequencies that we operate over in which we still have signal fidelity. And what do I mean by that? I mean that we haven't lost what is considered to be an unsatisfactory amount of signal, okay? So it's all dependent on this thing we call the cutoff frequency, which is not confusing because it's omega b, which is obviously for cutoff frequency. Don't confuse it with corner frequency, which is omega c, right? Think of it as omega b for bandwidth, right? The cutoff frequency is for bandwidth. What does the cutoff frequency tell us? It tells us the maximum input frequency at which the output of a system will track an input sinusoid with in a satisfactory manner. That sounds wishy-washy. What is satisfactory tracking? Who defines that? Right? Well, typically we say that it's when the amplitude ratio is reduced by a factor of 0.7071, which is also roughly 30% attenuation, right? So 29.39. 29. right? In dB, this attenuation 0.707, if you convert that to decibels, is 3 decibels. So we're saying that we want typically to find where we have a 3 decibel drop in our signal so that the bandwidth can be easily read from the Bode diagram. There's 2 steps. The first is read the low frequency magnitude on the Bode diagram, right? So at low frequency, read off whatever low frequency is. And step 2, subtract 3 dB from that, draw a line, see where that intersects your Bode diagram. All the frequencies from the starting point to the ending point, right, will, from the starting point to the cutoff frequency on the bandwidth, right? Because notice, bandwidth is a range of frequencies, right? Bandwidth is a range of frequencies. So bandwidth is all about, I don't want to lose too much signal, okay? I have a certain amount of signal tracking that I need, right? So let's go back to our low pass filter, right? I want to make sure that I'm okay with losing 3 dB, right? I can lose 30% of my signal and still track my input fairly well, okay? It's all about this range of signals that we can operate in, right? You're trying to give the range of inputs, the range of frequency inputs, which this is still accurate, right? Before we attenuate too much, right? So basically, under these conditions, right, you wouldn't want to operate, you wouldn't want an input frequency that's higher than your bandwidth, right? Because then you start to lose amplitude and your phase shift become too large. You're starting to set up this criteria for what is noise and what is not noise. And it is somewhat arbitrary, right? This is the typical that we use is 3 dB, but there's no rule that says bandwidth has to be 3 dB, right? Depending on your application, you might want a tighter bandwidth or a looser bandwidth, right? Depending on how accurate you need your tracking, your signal tracking to be. Right? How does this play into the bandwidth that you guys have on your home internet, right? Is that the same thing here? Well, kind of. Like that's more of a measure of, that's more of a measure of how much signal you're using, right? But similar, right? Because if you're playing, you know, if you're playing games and you have bad bandwidth, you're going to lag them, right? Depending on the game you're playing, that might be advantageous to you or not, right? Depends. So that's bandwidth, right? So let's here's our Bode diagram. This is our system that we were using, the 100, no, that's not that one, sorry. It's a new system. Notice our DC gain to start with, right? If we read this off, that's negative 36.3 dB. So the first thing about this Bode diagram is that at low frequency, we are already attenuating, right? We're already attenuating by 36 decibels here. So we want the bandwidth here. So we take that 36.3 and we subtract 3 dB from it, okay? And we draw our line all the way across, and where that intersects with our Bode diagram, we draw a line down, find the frequency, and now our bandwidth, right, is between 0 and 27 radians per second because our cutoff frequency is at 27 radians per second. Now, arbitrarily, let's do this example here. It's not really an example, more of a study, right? What if I have a magnitude plot that looks like this? That has some kind of weird looking double peak, Okay. Is this a thing that can happen? Yes, it is. If you have a fourth order system, it will have double peaks depending on where your natural frequencies are for both parts of the system, right? Because this one has some natural frequency that peaks here, and then there's another natural frequency here, right? So if you have them spaced out far enough in frequency, right? So if you have one at 10 and one at 1,000 radians per second, you would get something that looks kind of like this, right? So just for the sake of an example, right, here's 0. I'm going to subtract 3. Right, this is minus 3 dB, right? And notice what happens. I have a segmented bandwidth, right? Because this portion is all above my bandwidth. This portion is not. And then this portion is above my bandwidth also. So you actually have two sets of operating frequencies that are usable here. Okay. Now, for drawing purposes, in this class, we're not going to draw anything higher than a second order, okay? Because there's no reason. But if you ever see something like this, right, higher order systems, well, you can get them to do some pretty interesting things if you design them right. Okay? So you would have bandwidth in this range, but also here, right? So there's no, I guess the point of me showing you that is what? There's no hard and fast rule that says bandwidth is just one region, okay? There's no hard and fast rule that says bandwidth is just one region. Bandwidth is any point that crosses, that stays above the 3 dB line, right? Any set of frequencies that stay above the 3 dB line. Okay. Questions on bandwidth? John.
So that arrow isn't saying anything, it's the bandwidth arrow is just showing that entire region, it's not necessarily that has to be like.
Right, it's just saying that anything, well, yeah, anything under the curve here is the region of bandwidth because it doesn't dip below this 3 dB off DC gain until we get all the way out there. Any other questions? No? So you can do this in MATLAB. Here's some MATLAB code. You guys have seen enough of that sort of stuff. Let's talk about this, right? So what can we do? Well, we can plot a Bode diagram, right? We've talked about how to do this, but this is slightly different, right? You don't necessarily have to create the LTI system before going in. You can do something like this where you set up your numerator and denominator coefficients and just give Bode the numerator and denominator coefficients. You can also give it the LTI system though, right? So if you use the transfer function command and actually make it, you can just throw that in here as well, right? But it will do it automatically if you don't. I mean, that'll just plot a complete Bode diagram. We can also just have it give us magnitude and phase right off the bat. Right, and how we do that? Well, we set up our numerator and denominator like we do. We have to set a frequency that we're interested in, W in this case, or omega. And then we're going to use this version of the Bode command, right, where we have square brackets, mag, comma, phase, or whatever you want to call it, right? That's just names of variables. You can call it whatever you like. Mag, comma, phase is equal to Bode. Give it the numerator, give it the denominator, comma, omega, right? Or, right, if you'd prefer, right, where cis is equal to TF Yeah, I guess you could put the semicolon on this one too. Remember, if you put the semicolon on, we'll print it the screen. So, okay. This will give you, right, the magnitude in not decibels though, for some reason. It will already convert it. So if you want it in decibels, you have to do the conversion. That's what the final line in that section is. And then, can you do this using state space? Sure thing. You sure can. If you know A, B, C, and D, then you just give Bode A, B, C, D. Or you can create the LTI system using the SS command. Right? But if you have the transfer function or state space representation, you can do the Bode command. It's robustable. Smart enough to know what you're trying to do. All right? Hopefully it wasn't my mic. Hopefully I sound like Batman again. That was a fun day. Okay. Good. Everybody okay? Right. Remember in the homework, if you're asked to check something with MATLAB, don't just write, I checked this with MATLAB. Actually, like provide proof that you use MATLAB to check it.
For a Bode diagram, like if you're using Simulink, is there just like a Bode like command,
Oh,
like scope? Like is there a Bode equivalent?
no.
Oh,
It's a mess in Simulink. Just use MATLAB.
oh, okay, good to know.
Trying to do, so the thing is, Trevor, there's no need to do a Bode diagram in real time, right? Because the Bode diagram of the transfer function is never going to change.
Oh, that's true. Okay.
We will watch a lay video.
Welcome back to Control System Lectures. As always, if you have any questions or comments on what I'm about to say, please leave it in the comment section below and I'll address it. In this lecture, I want to present an introduction to frequency response methods, and in particular, I'm going to describe the Bode plot, how it's generated and used to visualize the frequency response of a system across the entire spectrum. I want to start by explaining another benefit of an LTI system. If you design a linear time invariant system, then there's only a limited number of mathematical operations that you can use. When building an LTI system, you can only use one is multiplication by a constant, the second is differentiation of the input signal, the third is integration of the input signal, and the fourth is adding two inputs together. Now you can always do division by multiplying by the reciprocal, and you can also subtract by adding a negative number. You might be wondering why it's important for me to start this lecture this way, and why bring up the fact that a linear system can only consist of these 6 operations. The answer is that when you subject a sinusoid to these operations, it doesn't change shape. And part of not changing shape means that it also won't change frequency. A sine wave input will always generate a sine wave output of the same frequency. In fact, the only 2 differences possible between an input sine wave and the output sine wave that's generated is the amplitude, which is the height of the sine wave, and the phase, that is shifting the sine wave in time. In fact, the sine wave is the only repeating waveform that doesn't change shape in a linear system. You can see here graphically what it means to change in amplitude and also to shift in phase. Let me give you a quick example so you can see what I mean. If we take an input sine wave and subject it to these 2 separate paths, the upper path is just multiplying it by a constant 2, and the lower path is integrating it, and then summing them together produces the output. If we make the input a pure sine wave of frequency 1/2 radians per second, then Then we could just calculate mathematically what the output would be. I'd like to make a quick note about frequency. I'm going to refer to frequency in units of radians per second, but this is proportional to hertz. So you can use either in this example. All right, back to solving this mathematically. The output would then be the upper path, which is a gain of 2 times the input, plus the integral of the input with respect to time. We can simplify this further by just taking the integral in the second half of the equation. Now, in order to interpret this from here, we're going to need some help from some trig identities. Now, I didn't remember this. I had to actually go look this up. But this trig identity that I'm going to be using is a sine of x plus b cosine of x equals the square root of a squared plus b squared times the sine of x plus rho, where rho is equal to the arctangent of b over a. Now, of course, this is only true if a is greater than or equal to 0. So let's apply this trig identity to our problem. In our case, a is equal to 2 and b is equal to negative 2. So the change in amplitude of the sine wave is just the square root of 2 squared plus 2 squared is the square root of 8 times the sine of 1/2 t plus the arctangent of 2 over minus 2, which is the arctangent of minus 1. If we write this in decimal format, this is just equal to 2.83 times the sine of 1/2 t minus 0.785 radians. Now, it should be obvious from this example that the sine wave that we input into the system is still a sine wave on the output. However, the amplitude has increased from 1 in the original input to 2.83. And that's the change in amplitude. And the phase has been shifted by 0.785 radians. Notice also that the output has the same frequency as the input, which is 1/2 radians per second. Now you could draw the input and the output in the time domain, and it would look something similar to the graph that we've done above. And that would work if you were only concerned with the response to a single frequency. However, more often than not, you're going to be interested in the whole frequency spectrum. So how can you visualize the gain and phase shift across the entire spectrum? Well, one way to do that is with the Bode plot. The Bode plot allows frequency response information to be displayed graphically on 2 separate plots, one for gain and one for phase, both of which are plotted against frequency on a logarithmic horizontal axis. But there's a caveat to plotting amplitude gain on a Bode diagram. We don't just plot the magnitude of the gain directly. First, we have to convert it into power, and then we represent the power gain in decibels, which is a logarithmic unit. To convert the amplitude to decibels, you first take the log base 10 of the ratio of amplitudes and then multiply it by 20. If you're confused about where this equation came from, let me just give you a quick history on decibels. When Bell Telephone Laboratories was trying to quantify loss in audio levels through telephone circuits in the early 20th century, they needed a unit of measurement and one that could cover a large range of audio power differences. Because the ear responds to sound pressure logarithmically, using a logarithmic scale corresponds to the way humans perceive sound. They created a measurement called the transmission unit, TU, where 1 TU equaled 10 times the log base 10 of the power loss, and this was chosen because it approximately was the smallest power attenuation detectable to the average listener. Now, to honor Bell Labs founder Alexander Graham Bell, they later changed transmission unit to decibel, or 1/10 of a bell, where bell is just the log base 10 of the power ratio. So to get from bells to decibels, you have to multiply by 10. Also note that power in a sine wave is proportional to the square of the amplitude of the sine wave. So now we can write the decibel equation with respect to amplitude squared, which is 10 log base 10 of the amplitude squared. And just because of the properties of logarithms, the exponential 2 just becomes multiplication, and you get 2 times 10, which is 20. So let's get back to plotting on the Bode plot. If we convert the gain from amplitude into decibels, we can plot the gain for that frequency omega. And for omega of 1/2, we can calculate the gain to be approximately 9 decibels. So on our gain plot, we could find where 9 decibels would be on the vertical axis, and where 0.5 radians per second would be on the horizontal axis, and put a little x there. You can do the same for frequency, but you first have to convert 0.785 radians into degrees because it's traditionally shown in degrees, and that's negative 45. This is the frequency response for a single sine wave. But remember, we're interested in plotting the gain and phase across the entire spectrum. So instead of running through the example above an infinite number of times, each at a different frequency, we could have just set it to a variable like omega and solved the system for any frequency. So if we had done that and we had a lot of time, we could have plotted a gain and phase plot that looks something like this for our particular system. And with the exception of being time-consuming, for this simple example, solving the response to the sine wave input was relatively straightforward. Well, except for having to remember that crazy trigonomic identity from earlier. There is a way of solving this without having to remember those identities and still produce the same relationship with frequency, and that's by referring to the system's transfer function. If we take the Laplace transform of the system above, the gain of 2 stays at 2, and the integral becomes 1 over s. Now writing the transfer function for a system like this can be done. The output y of t is equal to 2 times the input u of t plus u of t divided by s. A few algebraic steps here and you can solve for y of t over u of t, which is the transfer function, which is equal to 2s plus 1 divided by s. Recall that the Laplace transform s is a complex variable, sigma plus j omega. However, when we're talking about frequency response of a system, we are talking about the steady state response. That is, once all the transients have died out, or in other words, when the exponential term sigma is 0. So for steady state behavior, s just becomes j omega. Steady state phase and gain can be calculated directly from a transfer function by setting s to j omega. That makes the transfer function become 2 plus 1 over omega j, where 2 is the real component and 1 over omega is the imaginary component. If we then plotted these real and imaginary components on a real and imaginary axis, then we can calculate gain and phase geometrically from this plot. So here our real component is 2, and for omega of 1/2 from our example above, 1 over omega would also be, well, it's negative 2. I'm sorry, I made a mistake here. This 2 plus 1 over omega should actually be a minus because j times j is negative 1. So it's negative 2 on the imaginary axis for omega of 0.5. And if we draw a line from the origin of the axis to that point, then the length of the line is the gain of the system. And the length can be calculated by just taking the square root of the real component squared plus the imaginary component squared. This is just the Pythagorean theorem. And the phase is the angle between that line and the positive real line. And you can solve for this using the arctangent. I'm using arctangent 2 in this case only because it keeps track of the sign of the inputs, and so you don't have to worry about whether A is positive or negative like we did up above. So again, the length of this line is the gain, and the angle off the positive real line is the phase. So you can see in this example that the real component doesn't change with frequency, only the imaginary component. And if we sweep through frequencies from near 0 all the way up to near infinity, you can get a visual understanding of what the gain and the phase are doing for this particular system. At omega of near 0, the imaginary component is almost infinite. And at an omega of near infinity, the imaginary component is near 0. And if you drew that red line from the origin, starting with omega of 0 down at near infinity, which would be a near vertical line, infinitely long, you would see that they would get shorter and shorter and shorter and shorter, and finally ending with a length 2. If we go back up to our plot, you can see that's exactly what the gain is doing. The limit as frequency approaches infinity goes to 6 dB, which is a gain of 2. And off to the left, as frequency approaches 0, the gain goes off to infinity. Also, if you look at phase here, you can see that phase starts out at negative 90 degrees and then goes to 0 degrees. And again, that's exactly what our plot is doing. And that's how you can represent a large amount of frequency response data through a system. In fact, that's exactly how graphing programs such as MATLAB would calculate the Bode plot from a transfer function. Doing this by hand, though, still seems like it would take a long time. But luckily, there is yet another way to graph the frequency response across the spectrum. And not only is this a much faster way, but it also gives you an intuitive understanding into the frequency response of the system, and you do this only by looking at the transfer function. By following a few rules of thumb, you can graph the Bode plot by hand using straight line representations, and I'll show you that in the next video. For now, as always, thanks again for watching, and don't forget to subscribe.
All right. All right. In the class, we'll watch the second part of that, right? Because that video took us up through steady state response, right? Kind of rehashed how we got to steady state response, talked a little bit about how to do Bode plots, right? But that was mostly how do we draw them if we're going to sweep through all frequencies. The next one is going to be more about asymptotes. Before we get there, we're going to talk about vibration. Right? So, vibrations, right? Vibrations in mechanical systems are typically an undesirable phenomenon, right? They transmit forces, they generate noise. Why? Why don't we want vibrations? What's wrong with having vibrations? What makes them undesirable?
It can cause problems in the system, like material fatigue, material being
Sure, material fatigue, things getting knocked out of place, like screws backing out, right? We've all seen that. This system right here, that screw backs out all the time. You can't run it for very long. The electromechanical system lab, because somebody didn't use a left-handed thread. Dr. D. But anyway, what else? Right. So those are two big ones. What else can arise? Right. One of them's written up there. Right?
Could they cause unstable oscillations, like when the bridge collapsed in California?
Yep. Verrazano Narrows Bridge, right? Sorry, Tacoma Narrows Bridge. That's one. Not Verrazano Narrows. That one's in New York. That didn't fall down. Tacoma Narrows Bridge, right? Shook itself right into the history books, right? Yeah, fatiguing, cracking, crack propagation, screws backing out, noise, right? We don't like noise in our system, right? Noisy measurements are annoying. Luckily for us, suspension systems can be used to isolate vibrations to and from an object, right? These vibration isolation systems come in two flavors. The first is that they reduce the transmission of vibrations from a machine to the environment. So something that is shaking wildly and we don't want it to affect the rest of the surrounding area, right? For example, machines in the machine shop, they tend to vibrate, but we don't want all of the machines at the machine shop to vibrate. So we isolate that through suspension mounts, right? We also want to reduce, there's also the other way, right? We want to reduce the amount of vibration that comes from the environment into a machine, right? That's how your car suspension works, right? The road is bumpy. You don't want the people inside to feel the bumps. So we have car suspension, which smooths out the ride, right? It's also why we have the SEM table project, right? The vibration dampening table senior project that some of you guys are working on. Specifically, the scanning electron microscope requires that we, because it looks down at such a small scale, any stray vibrations causes the field to move wildly, right? And so we are having some of you guys build a vibration dampening table for it. So let's talk about vibration isolation, right? So in this case, right, we've got vibration mounts, suspension mounts, whatever you want to call them. And a vibration mount is essentially just a spring mass damper system, right? It's a spring damper system. It's a shock, right? It's a shock absorber. So what happens? We have some base motion here, right? The bottom's moving, and we want to attenuate that signal, right? We want to limit the amount of vibration that the actual machine itself sees, right? So our goal here is to reduce the amount of motion that is transmitted from the base to the instrument. And so we want to filter this out, right? We're building a mechanical filter. This idea is called transmissibility. And the transmissibility of a system is the measure of how good it is at suppressing or attenuating vibration. A large transmissibility number is bad. We want a low transmissibility number, right? A large transmissibility is bad. It means that you will amplify your vibration. Transmissibility for displacement excitation is defined as the ratio of the transmitted displacement, or the output, to the input displacement amplitude. That sounds very familiar. The ratio of the output displacement to the input displacement amplitude. That sounds really familiar. It sounds almost like a transfer function, right? Sounds almost like a transfer function. It's not exactly a transfer function, but it sounds like the transfer function where we're looking at the amplitude ratio, right? Oh, we talked about amplitude ratio, right? We talked about amplitude ratio. Isn't that just the magnitude of my sinusoidal transfer function at a specific frequency? So it turns out that the transmissibility is just another way for us to package the magnitude of a system from the Bode magnitude plot. Transmissibility for a force excitation is given as this equation, where we have the transmitted force amplitude divided by the input force amplitude. Okay. F of t over F in. Now, I want you to notice something about how we measure transmissibility. We don't care about the frequency that we're operating at. Neither of these take into account frequency. What matters is the amplitude, right? We are saying that I don't care how much phase lag I'm introducing into this system. All I care about is that I get those vibrations minimized. That is what this is saying. Right, so let's talk about this through an example. Here we have our standard second order system. In this case, it's free end, right? How do I know that? Well, it's got minus x dot, right? So the base is moving and the object is moving. So there's relative distance between the damper and the spring, right? And we have mx double dot plus b, x dot minus x dot b plus kx minus xb is equal to 0. We rewrite it as our input-output form. We get mx double dot plus bx dot plus kx is equal to bx dot b plus kxb. Find our transfer function, right? And there it is. And then we rewrite it in the standard form, right? Then we just rewrite it in standard form. I'm just rewriting this in standard form. Great. Great. So far, this is just stuff that we've done already before, right? So what makes it different? What makes it transmissibility, right? Well, what makes it transmissibility is what we're about to talk about, right? We're gonna make this into the sinusoidal transfer function, right? And here it is. And then we're gonna algebra it up. And we're gonna make some substitutions. And instead of k over m, I'm gonna use omega n squared. And instead of b over m, I'm gonna use 2 zeta omega n, and I'm going to algebra it. And thank you. No, wrong way. I'm going to get this right here. This equation. G of j omega is equal to 1 plus j, 2 zeta omega over omega n over 1 minus omega squared over omega n squared plus j times 2 zeta omega over omega n squared. But we're not done yet, not done quite yet, right? Because we need to take the magnitude of this in order for us to get the transmissibility. So let's do that. And if I do that, I'll get this expression. But then I'm also going to say, well, you know what? I have this ratio omega over omega n. And I'm going to call this the frequency ratio. And I'm going to call it beta. Right? So now beta is omega over omega n. And I substitute that in. And so my transmissibility is a function of zeta and beta, my damping and frequency ratios. The frequency ratio is the ratio of my input frequency to my natural frequency, right? So what does this mean? Right? What does this mean? Well, we're going to plot this. We're going to plot this for all beta, for different betas, as beta increases from 0, right, all the way up, well, near 0, right, because beta of 0 would be very interesting, because we have an input frequency of 0, which is just 0. But we're gonna plot beta from low and increasing, and we're going to plot different zetas values as well, and we're going to see what happens, okay? Because what is transmissibility? Well, it's a measurement of essentially how we're scaling our input amplitude, right? It's essentially what it is. So let's plot it. So right here on the y-axis, I've got transmissibility. And on the x-axis, I've got beta. And each one of these lines represents a different zeta, right? The cyan one is zeta is equal to 0. The red one, zeta is 0.2. The green one is zeta is 0.5. And the blue one is zeta equal to 1. Okay? So the first thing you probably notice is that we get large spikes right before beta is equal to 1, right, for most cases. Right? So we get this big peaks. And you're kind of probably thinking, at least I'm hoping that you're thinking, that this kind of looks like the magnitude portion of a second order system magnitude plot, right? Where we had that one that had all the zetas. Maybe you don't remember. We only had it on screen for a second. But that's essentially what this is, right? This is just the magnitude, just not in dB, right? This hasn't been converted to dB. So if you wanted to know the transmissibility of something by looking at the Bode diagram, you'd find out what the phase, or not the phase, I'm sorry, what the magnitude is at a specific frequency, and then you would pop it out, right? By pop it out, I mean convert it from dB. Anyway, here we are, right? So what are some notes here? Well, first of all, the transmissibility depends on the damping ratio and the frequency ratio, right? We knew that from the equation. Secondly, when zeta is equal to 0, right, which means we have no damping, then my transmissibility is infinity when beta is equal to 1. So when beta is equal to 1, omega n is my resonant frequency, right? This is the Tacoma-Narrows bridge, right? If we operate near resonant frequency, we get an amplification of our vibrations, right? And if you don't change that, you will continually amplify your vibrations until you shake it apart. Right? This is why mechanical and biomedical engineers don't like to operate near natural frequency. This is also why electrical engineers like to operate near natural frequency, because in certain electrical applications, having that much amplification is advantageous, right? In a mechanical system, it is not. Causes problems. But anyway, right? So when beta is equal to √2, which is like 1.4-ish, right? The transmissibility is equal to 1 for all cases. Doesn't matter what zeta is. When beta is equal to √2, the transmissibility will always be 1. right here. Root 2. Right there, right? This point, everything at that point right here, right here, all transmissibilities of 1. What does a transmissibility of 1 mean? It means we are neither attenuating or amplifying our signal, right? It is the same as it came in as. It's a scaling factor of 1. Right? The transmitted amplitude is equal to the base amplitude without gain or loss if the input frequency is equal to omega n times root 2. What about when beta is very small? Well, hey, when beta is really small, which is the same as saying that we have a very stiff spring, right? Meaning that omega n is much larger than omega, right? Then our transmissibility is approximately 1 for all zeta, right? So on the left-hand side here, right? Yeah, do it that way. Right here, everything's about 1, right? For low beta. When the input frequency ratio is beta less than root 2, right? So when we're in this portion of the plot, from here to here, right? Beta less than root 2. If we increase zeta, we decrease the transmissibility, right? So that's pretty easy to see here, right? If we start with the cyan line and we work our way down, the dark blue line has the most damping ratio, and it also has the lowest transmissibility. It's also greater than 1, but it's not as bad as running no damping, right? And I think this kind of makes sense from a physical standpoint in the fact that the more damping we have, the harder it is going to be for us to move, right? Think about the door closer, right? If you cranked up the damping in there, right? It's harder for you to push it, right? When the input frequency is beta is greater than root 2, right? So the right-hand side here, show with this blue line, from here to here, right? This region, greater than 0.2 or root 2, increasing zeta degrades vibration isolation. So it reverses, the trend reverses at this point. So if you are operating, right? So if your goal is to reduce the amount of vibration in a system, and you know that you are operating in a range in which beta is less than root 2, right? You want the highest damping ratio that you can possibly get, because that is going to minimize the amount of vibration, but it's still not going to attenuate your vibration. If you want to attenuate vibrations, you need to be operating in the greater than root 2 region, right? Because everything that's greater than root 2 is TR less than 1, right? But in that case, you actually want less damping ratio. You actually want less damping ratio, right? The trend flips at the root 2 point, okay? Transmissibility will only be under 1 when beta is greater than root 2. Only. Right? You can see it from the plot, right? See it from the plot. Right? Oh, is that too much? Oh, things are happening. All right. So, if we want the minimum amount of transmitted force or displacement, we need to choose vibration isolation mounts with an undamped natural frequency that is much lower than the expected input vibration. Why? Because that drives beta up. The lower omega n is, the higher beta will be, right? because the smaller the denominator is, the larger the fraction is, right? So if we're designing a system, right, and we want to minimize vibration, we want to pick omega n much less than omega, right? But this is also a way of saying that we want to pick k over m. That ends up being much, much less than omega, right? Because natural frequency is determined by physical properties of the system. And you might not be able to change the mass, right? The mass might be set, but you can probably change k, right? So if we wanted to minimize omega n, we would want to minimize k, right? Once we have those two things settled, right? If it's possible, and we know that beta is greater than root 2, we want to pick something that has zeta that is low, right? Right? So we already know omega n, we settled on our k. Zeta, or B, right, our damping coefficient, is a function of mass, spring constant, right, and zeta. If we already decided on k and m, then we can tweak B, or we can tweak zeta, either one, by tweaking B, right, or vice versa. So all of these physical parameters that we've been talking about, Bm and K for a mechanical system, they all tie in and they affect how our vibrations are transmitted, right? And in this case, if we wanted, right, let's solve this for zeta, just because. Sorry. Right? If we wanted to minimize zeta, we would also have to minimize B, right? If we wanted to minimize zeta, we would have to minimize B. That is if we already know that beta is greater than root 2, which is what we should be shooting for, right? Because that's the only place that we can attenuate these vibrations. Does that make sense? That makes sense? Everybody tracking? You guys have any questions so far on transmissibility? Oftentimes, the disturbance that you're applying to the system or the input frequency might not be constant, right? And I think, I keep going back to the example of your car and suspension, right? But all asphalt is not poured equally, right? All road surfaces are certainly not the same. And your car needs to be able to handle a range of road surfaces, right? So in some cases, you might have to accommodate a range of input frequencies. I know that this system is going to run, like, maybe you're using the bandwidth as your range of frequencies. I don't know. But you know that there's some range of frequencies that you're going to be operating under. You need to make sure, you have to see how beta changes for all of those and how that affects your transmissibility. Turns out that just like everything else in designing a system, there is this trade-off. The trade-off is you might, in order to hit transmissibility requirements, you may have to compromise on other design constraints like shock response, settling time, things like that, how much overshoot you have. right? So the frequency response might directly affect your time domain response, right? And vice versa. Both of these things, are not, they're mutual, right? They both exist in parallel. They're not one or the other. You have both working at the same time. We're not going to watch that video. It's not a good one. I regretted showing it to the other class this morning. But Dr. D, didn't you watch it before? Yes, I did. But I changed my mind on it. People are allowed to change their minds. Jeez. Guys are being harsh today. Is it because I told you about spring break? That's not my fault. I told you it's Dr. Staggs' fault. All right.
Welcome back to Control System Lectures. Just to let you know, I've decided to drop the prefix on the video titles because they were taking up too much real estate. But these videos are in the same series of lectures, so if you're subscribed to Control Lectures, you'll still receive these updates. This video is a continuation of the Introduction to Bode plots that I posted last week, and here I'll discuss how to sketch a Bode plot by hand directly from the transfer function. And this first video will only cover when the transfer function is a constant gain. Now you might be asking yourself, why do we need to learn how to sketch Bode plots by hand when we have computer programs such as MATLAB that can generate a Bode plot with the touch of a button? I've been a controls engineer for over 10 years now, and to be honest, I very rarely ever had to sketch a Bode plot by hand. But while you might never actually need to do this, there are still at least two compelling reasons to learn this skill. The first is that by practicing this, it gives you an intuitive understanding of how poles and zeros affect the frequency response of a system without having to actually ever plot the response. And the second is that it gives you the ability to estimate the transfer function just by looking at the frequency response of a system. And this is particularly handy when you're trying to estimate a transfer function, say from the output of a frequency sweep on a new structure that you're building. So recall now from the introduction to the Bode plot video that when you have a transfer function h of s, you can calculate the steady state frequency response by setting s to j omega. Then you can solve for the real component and the imaginary component and rewrite h of j omega as just the real component plus the imaginary component times j. If we were to plot this on a real and imaginary axis, where the real component is just drawn on the horizontal line and the imaginary component is drawn on the vertical line, the gain of the transfer function for that particular frequency is just the length of the line from the origin to that point on the real imaginary axis. That can be written as the square root of the real part squared plus the imaginary part squared, or in shorthand notation, you can just put these two vertical lines around it, which means the magnitude of h of j omega. And the phase is just the angle of the vector off the positive real line. And we can write this as the arctangent 2 of the imaginary part and the real part. And in shorthand notation, you can just write this as the argument of h of j omega. We can establish the sign of the phase by which side of the real line it appears on. In this case, it might be about 45 degrees. If we continue it a little bit further, it might be 120 degrees. But if we go down below the real line, then it becomes negative, so negative 60 degrees in that case. So let's review the simplest transfer function there is, which is a constant, and see how that is represented on a Bode plot. In this case, the transfer function h of s is just equal to k, which can be any real number, either positive or negative. And we can represent this in block diagram form by showing that the input gets multiplied by k and becomes the output, or u of s is the input and y of s is the output. Now we can apply the gain equation from above, which is the magnitude of h of j omega, to this constant k, which is just the magnitude of k, which is a positive k. And the phase, which is the argument of h of j omega, is equal to the arctangent 2 of the imaginary part, which in our case is 0, and the real part, which is k. And again, k can be either positive or negative. And that's why we're using arctangent 2 to keep track of the sign. Let me explain it this way. If we were to plot this on the real and imaginary axis, then all of the values would lie on the real line since there is no imaginary component. If k is a positive number, then it'll appear on the right side, and if it's a negative number, it'll appear on the left side. But one thing to note about both of these positions is that whether k is positive or negative, the point still exists exactly a k distance from the origin. And since gain is the distance from the origin, the gain is always k for constants, whether they're positive or negative. Phase, on the other hand, is different. For the first value, a positive k, phase is 0 degrees. But for a negative k, it's 180 degrees off the positive real line. Traditionally, we would just say minus 180 degrees, but they're equivalent. So if the constant is positive, then the phase is 0 degrees. And if the constant is negative, then it's minus 180 degrees. And that's why I like to use arctangent 2, because it keeps track of the sign of k for you, so you don't have to think about that. If you just use arctangent, you'd have to remember to subtract 180 in certain cases and not in others, but I'd prefer not to remember that and just use arctangent 2. So now that we have our gain and phase, how can we represent this on a Bode plot? Well, the gain is easy. Like we said before, it's just k for all frequencies. But to plot it on a Bode plot, we have to convert it into decibels, which is just 20 times the log base 10 of the magnitude of k. And again, it's constant for all frequencies, so it's just a horizontal straight line. And luckily for this example, phase isn't much more difficult. Phase is 0 degrees when k is positive, and it's minus 180 degrees when k is negative. But again, the phase stays constant either at 0 degrees or at minus 180 degrees. It stays constant across all frequencies. So if it's not too intuitive looking at this at a Bode plot or on a real and imaginary axis, another way to think about this is just to input a sine wave through the block diagram. A sine wave input produces a sine wave output whose amplitude has been adjusted by a factor of k. Also, if the input was a positive sine wave and the k was a negative 1, the output would just be flipped along the vertical axis like this. Of course, as you can see, this is just a phase shift of negative 180 degrees. So let's do one last example, and this is with a very simple electrical circuit. Let's say you had a voltage generator whose output was a sine wave. And the positive voltage was then applied to a resistor, and both of them were tied to ground. The resistor has resistance R. A current would be induced, I, and using Ohm's law, we know that V equals IR. But if we wrote this as voltage changed over time, it would be V of time equals I of time times R, since resistance wouldn't be changing. We could take the Laplace transform of this equation and then solve for the output I over the input V and get 1 over R, which is the transfer function for this simple circuit. And since the resistance isn't changing with time, 1 over R is just a constant, and we could represent this on a Bode plot as a constant gain at 1 over R with a phase shift of 0 degrees. I know it's 0 degrees because R is going to always be positive. So this is what the Bode plot would look like for a very simple constant transfer function. Of course, most transfer functions aren't this simple. They can be made up of any number of complex or real poles and zeros. But the step-by-step example here of how we go about generating a Bode plot still holds up for those other parts. And so what I'll do in the next couple of videos is expand on all of those different types of transfer functions and then show you how to approximate them very easily using just a few simple concepts. And since the next few videos all tie together nicely, I'm not going to wait a week to put them out. I'll try to get most of them out over the next couple days. So if you don't want to miss anything.
All right, so that's that. Like I said, we're not gonna watch this video. I don't think it's value add. So we're just gonna be done for today. It's gonna be it. That's all I've got. Next class, we're gonna talk more about rotating on balance, and we're gonna do some problems. That's about it. We'll probably watch another Bode plot video because reasons. for recap purposes, right? But we're going to focus on problems. And then next week, we're going to likely go through a case study that will hopefully tie everything that we did from the beginning of semester until now all together. Okay. That's the semester, people. See you guys on Thursday.